Okay, let me make the diagram first and then we'll discuss the problem. So you have some cylindrical pulley. So there is a pulley here, you have attached. So this is the pulley, circular. Maybe I am not able to make the circular. And there is a mass that is attached here. And this mass, they call it A. And this point is O. This is the vertical. From vertical there is angle alpha. At this angle there is a mass M. So this mass is M. This radius of this pulley is R. This is figure 4.17. Now let me read the question. A uniform cylindrical pulley of mass capital M. So pulley has mass capital M. Radius R can freely rotate. So radius is R. Can freely rotate about a horizontal axis O. So there is a horizontal axis. About this axis it can rotate freely. So it can rotate freely. The free end of the thread is tightly bound to one pulley and a dead bit. So this thread has been tightly bound over this pulley and there is a dead bit A. At certain angle alpha, it counterbalances the point mass M fixed on the rim. So there is a mass M that is fixed on the rim. So there is a mass M that is basically you can see this is belted on the rim. Now this mass and this mass are basically counterbalancing to each other when the angle is alpha. You see what will happen. This mass will try to rotate this side and this mass will try to rotate this side. So there will be angle alpha at which the system will be in equilibrium, that is in the rest. Find the frequency of a small oscillation of this arrangement. So we have to find out the frequency. So this means I have to find out the time period. If I know the time period, I can find out the frequency. Now how will it work is, first you have to write down the equilibrium condition. So let us say mass of A is not given to you in this problem. This means in the last it has to be cancelled out. So let us say mass of A is M0. So mass of A, I am assume this is M0. So what are the forces that is acting? This side will have M0 Z and there will be a tension T. There will be a tension T also. Now this pulley, this force mg that will act in this direction. Now I can write equilibrium condition. So that is the equilibrium condition will be what will the equilibrium condition in this time? This equilibrium condition will be not obtained by summation of forces is equals to 0. This time it will be obtained by summation of torque is 0 because this system is in the rotational equilibrium. When your system is in translational equilibrium, we write summation of forces is equals to 0. When your system is in rotational equilibrium, we write summation of torque is equals to 0. This means this time this side torque is equals to this side torque. So mg, this length is what? This is alpha. So this is r sine alpha. Are you getting? I think all of you understand. This line is, this length is r. So if you drop a perpendicular from here, that will give you torque. This will be r sine alpha. So I will have a torque this side, that is mg into r sine alpha. And this is equals to torque this side, and this side torque is T into R. Are you getting? Now I can write another equation from this because this is also in translational equilibrium. So T is equals to m naught z. Are you getting? T is equals to m naught z. And if I plug the value of T here, I will have So GR goes out through earth. So I will have m naught is equals to m sine alpha. So this is my equilibrium condition. Let us call this as equation 1. Now my target is, if I displace the m naught by distance x, what will be the resulting forces that will act, to find out the equation. So let us say initially this was making an angle alpha. Now what we have done is, I have displaced this mass by distance x downward. So initially it was here, now it is here, and this is displaced by distance x. Are you getting? If this goes this side by x, this means this mass that is here will also go up by r into theta, and x is equals to, so this will go up by distance x, and x has to be equals to r into theta. So let us say this angle is theta, so theta will be given by x by r. I think all of you are able to understand this one. If you are not able to understand, let us see. So let us see this. If I try to pull this side, what will happen? This disc will rotate, and how much it will rotate? Since this side, this has gone by distance x, this is a case of pure rolling, so this goes by x. So this length, linear length, I can say this go by x, and in terms of angular, so this x should be equals to r into theta, so theta will be x by r. Now again, I don't have to do anything. So let us say this mass is going downward by acceleration a, and this is rotating with angular acceleration alpha. This is the case of pure rolling, so this point will have acceleration alpha into r, or this point I can find from the thread will have acceleration a. So now I can write condition for pure rolling. I will have a is equals to r into alpha. Now if I write equation for this object, weight is acting m naught g in the downward direction, tension is acting in the upward direction. Here also I will have tension. Are you getting? So I will have, in the downward direction you will have m naught g minus t will be mass into acceleration. Now this time acceleration is in this direction and x is also in this direction, so I have to write d2x will be dt square, no negative sign. Let us call this as equation 2. Now let us frame equation 3, and that will be formed from rotational motion. So you see, the force is acting on the disc. I will apply torque is equals to I alpha for the disc, and the mass of the disc is given to you m, and so if I know mass and radius, I can find moment of inertia of the disc. So let us say disc has moment of inertia I. We'll find this value. So what are the torques that is acting? So let me make another diagram. So the torques that is acting on this is, this side will have angle. So this angle you have alpha plus theta. Initial angle was alpha. Now this will be alpha plus theta. Are you getting it or not? So this angle is alpha plus theta. But the forces that is acting, so this mass is m. So this is mg. This side you will have tension. And this is rotating in this direction by angular acceleration alpha. And alpha is nothing but a by r. So if I write this in this direction, total torque is, so T into R. So T into R minus mg, and this length will be mg r sine alpha plus theta. So this will be r sine alpha plus theta. Are you getting? This is equals to mass into acceleration of the disk, I alpha. So I for the disk is I, and alpha is a by r. So I can modify the same equation. I can write simply T r minus mg r sine alpha plus theta is equals to I by r, and acceleration will be d2x by dt square. So let us say this is equation number 3. If I divide by r, I can write the same equation. T minus mz sine alpha plus theta is equals to I by r square d2x by dt square. Now let us write equation number 2 and equation number 3 together and add those two equations. Equation number 2 you have m naught z minus t is equals to mass into acceleration, so m naught d2x by dt square. So this is the equation number 1 you have. Now if you add these two equations, what we'll have, tt goes out, so we'll have m naught z minus mg sine alpha plus theta. This is equals to m naught plus I by r square d2x by dt square. Now I will write sine alpha plus theta into sine a cos b. So this is m naught z minus mz sine a plus b sine a cos b. So sine alpha cos theta sine a cos b plus cos a sine b. So plus this will be minus mg sine a cos b cos a sine b cos alpha sine theta is equals to m naught plus I by r square d2x by dt square. Now the angle theta is small, I will use the first approximation. If theta is small, sin theta can be written as theta and cos theta can be written as 1. So this term will be 1 and this term will be theta. Are you getting? So you will have m naught z minus mz sin alpha, because cos theta is 1 if the angle is very small, minus mz cos alpha, and sin theta will be simply theta. So this is theta is equals to m naught plus I by r square d2x by dt square. Now if you see, this condition is same as equilibrium condition. You check this equilibrium condition, so this term will be 0. You see, you have equilibrium condition is m naught is equals to m sin alpha. So if you see this value m naught, g if I take common, so m naught is minus m sin alpha. So this will 0 from equilibrium condition. So this is 0 from equilibrium condition. This term will always be 0. So if you are doing some mistake, then in that case it will not be 0, otherwise it has to be 0. Because this side I will only have a term that depends upon theta. So now I will have minus mz cos alpha into theta is equals to m naught by plus I by r square d2x by dt square. Now I have also written x is equals to r theta, so I can replace theta. So if you remember, x is equals to r theta, so I can eliminate theta from here, so it will become minus mz cos alpha. Theta is x by r. Are you getting? So I can write theta is equals to x by r, and if I take r that side, let us write x by r, and this is m naught plus I by r square d2x by dt square. Now we also have mass of m is, I can write in terms of m naught. M is m naught by sin alpha. So let us plug this value. M is m naught by sin alpha. So this is m naught by sin alpha into z into cos alpha x by r m naught plus I by r square d2x by dt square. Basically m naught is unknown. I have to write in terms of m. So this is unknown. So I want to write in terms of m. Equilibrium condition is m naught is equals to m sin alpha. So what we will do is I will eliminate m naught. So m naught is here. So let us say this equation I can modify again. This equation I will place the value of m naught because m is known, m naught is unknown. So I can write minus mg cos alpha into x by r. This is equals to m naught is m sin alpha. And the disk has a moment of inertia. So this is a solid cylinder. So moment of inertia will be mr square by 2 because this is a solid cylinder. So I can plug this value here. So mr square by 2 r square. So this is r square is here. d2x by dt square. Are you getting? So you will have, so I think you will have minus mg cos alpha by r into x. This is equals to, so r square goes, so you will have 2m sin alpha plus capital M, this divided by 2. So let us take 2 that side, d2x by dt square. I can also write d2x by dt square. This will be 2 goes this side, so we will have 2mg cos alpha by r, and this divided by 2m sin alpha plus capital M into x with a minus sign. Are you getting? There is a mistake in finding the moment of inertia. Can anybody tell me what is the mistake? The mistake is finding the moment of inertia. What is the mistake in finding the moment of inertia? Let us think and tell me what is the mistake. There is a mistake because your disk, I said the moment of inertia of the disk is I, but disk also contains mass m, a small mass. So this mass will also contribute to the moment of inertia. So moment of inertia will be mr square by 2 plus a small mr square because this has a distance r. So the moment of inertia of this small mass about this point will be mr square, and the whole disk will have a moment of inertia as mr square by 2. So I have to add a term, this plus mr square. Are you getting? This is the important one. So let me write here. So I in this case will be mr square by 2 plus mr square. Are you getting? Now if you see, I can do this correction. So this is mr square by 2r. So I is m by r square plus mr square. So simply I will have one m term that will be added. In the top also you will have one m term that will be gets added. Are you getting? Here also you will have one m term that gets added. M or 2m. So basically we will have 2m because this 2 will be multiplied. So we will have 2m. So this 2m gets added here also. I can write in a better way again so that you don't have any confusion. So I will have d2x by dt square. This will be minus 2mg cos alpha divided by, this is r, and 2m plus 2m sin alpha, so I can take 2m common. So I will have 1 plus sin alpha plus capital mass M, and this into x. So if you solve for omega, so omega will be under root 2mg cos alpha divided by m plus 2m 1 plus sin alpha. So you can find out the time period because you know the omega. So important point in this question you have is writing the equilibrium condition first, and then you have to also consider the moment of inertia of the small mass. So in finding the moment of inertia, you have to be careful, not like me. You have to be very careful to add all the moment of inertia. Moment of the inertia of disk plus moment of inertia of mass that is attached to the disk. That is I is equals to mr square by 2 plus mr square, a small mr square. Now the third important point we have, that is the writing the rotational motion, that is the torque is equals to I alpha. In this case again we will have a pure rolling, that is x is equals to r theta. Another equation you will find from translational motion of mass m naught, and you have to eliminate m naught because m naught is unknown. You have taken this value, mg is given, so you have to eliminate m naught in terms of m, and we have already found this m naught from equilibrium condition. M naught is equals to m sin alpha. So from there you can find m naught, and if you do calculation in a good way, you will get this answer. We'll discuss the next problem.